So for this example, it's asking us to find and classify all relative extrema and saddle points for this equation. So our equation is f of x and y is equal to 2xy minus 1/2 of x to the fourth plus y to the fourth plus 1. So the first step we got to do in order to solve this problem is take our partial derivatives and sum up our gradient. So partial derivative of x. Partial derivative of x, 2xy, y we ignore, so 2x, derivative of x is just 1, so it's just going to be 2y, minus 1/2 on the outside, and we take the derivative of the inside with respect to x. So x to the fourth, the derivative of that is just going to be 4x cubed. This is going to be treated as a constant, and the derivative of a constant is 0, so it's going to be 0 for the y to the fourth. This is a constant 1, so it's going to be also 0. I'm going to simplify this a little bit better. So I'm going to have this as 2y, 4x to the cubed power times 1/2 is going to be 2x cubed. Partial derivative of y. It's going to be very similar. So 2xy, the partial with respect to y, is going to be 2x minus 1/2 on the outside. Derivative of the inside with respect to y. X to the fourth is going to be treated like a constant, so it's going to be 0. So y to the fourth, the derivative of that is going to be 4y cubed. Derivative of a constant is also 0. So if I take this over here, 2x, 4y cubed times 1/2 is going to be 2y cubed. So my gradient is going to be equal to 2y minus 2x cubed on the x side, and for the y side it's going to be 2x minus 2y cubed. So I'm going to set this as a piecewise function. So up top I'm going to have 2y minus 2x cubed, and I'm going to set this equal to 0. Over here I'm going to have 2x minus 2y cubed is also equal to 0. And I'm just going to simplify this a little bit more. So I'm going to have 2y, and I'm going to take the negative 2x cubed over the other side, so it's going to be equal to 2x cubed. If I divide both sides by 2, this is going to equate to y is equal to x cubed. Over here, if I take 2y cubed onto the other side, I'm going to have 2x is equal to 2y cubed. And same thing here, if I divide by 2 on each side, I'm going to have x is equal to y cubed. So what we just did right now, we solved for the two equations of the graph that we're going to have, and from that graph we're going to solve our critical points, or solve for our critical points. So here is the graph. Okay. So the graph of y is equal to x cubed is going to look like this. And then x is equal to y cubed is going to look like this. So our critical points are going to be right here, and right here. This value is going to be -1, -1. This is the origin 0, 0. And this is going to be 1, 1. And another way to see this is if I have y is equal to x cubed, if I plug in 1, 1 is equal to 1 cubed, that's equal to each other. If I plug in 0, 0 is equal to 0 cubed, which is still 0, so that checks out. And if I have -1 in here, -1 is equal to -1 cubed. -1 cubed is -1, so this also checks out. So this proves that these are my critical points: 1, 1, 0, 0, and -1, -1. So the next thing we're going to do is we're going to plug these values into the Hessian matrix, but before I do that, I have to get the rest of my partial derivatives. So we said over here that my partial derivative with respect to x is going to be 2y minus 2x cubed. So my second partial derivative with respect to x is going to be f of xx, and that's going to be just partial derivative of -2x cubed, which is negative 6x squared. My partial derivative of x with respect to y. So I'm going to look at this equation, ignore this, treat it as a constant. So that derivative of 2y with respect to y, that's just going to be 2. My first derivative of y, we said earlier, was 2x minus 2y cubed. So my second derivative with respect to y is going to be negative 6y cubed. The 2x is treated as a constant since it doesn't have a y variable in it. And if I have my second partial derivative of y with respect to x, so f of yx, it should be the same thing as f of xy, which is 2. And you can see it right here. Partial derivative of 2x, that's going to be 2. So those are the values I'm going to have in my Hessian matrix. So the formula for the Hessian matrix is simple. You're just going to have a matrix, a 2 by 2 matrix. So I'm going to have my first double derivative of x with respect to AB. Over here I'm going to have my f of xy with AB. Over here it's going to be f of yx, and we said earlier it's going to be the same value of xy. And then my second partial derivative with respect to y. So the first thing I'm going to have over here is at the critical point of 0, 0. And I should probably label my critical points over here. So I have 0, 0, negative 1, and 1, 1. Okay? So at 0, 0. So my second derivative with respect to x is negative 6x squared. If I plug in 0 in there, it's just going to be 0. My f of xy is equal to 2. My f of yx is also equal to 2. And my second partial derivative with respect to y is negative 6y cubed. If I plug in 0 into that, it's going to be 0. So if I solve this matrix, 0 times 0 is 0. 2 times 2 is 4. Take that from 0, so 0 minus 4 is equal to negative 4. Negative 4 is less than 0. So this tells me that it's a saddle point. Saddle point, right off the bat. When I try it at the value 1, 1, so my second partial derivative with respect to x is negative 6x squared. If I plug in 1 into that, I'm going to have negative 6. F of xy is 2. F of yx is also 2. And f of yy is negative 6y cubed. If I plug in 1 into that, I'm going to have negative 6. So negative 6 times negative 6, that's positive 36. 2 times 2 is positive 4. 36 minus 4, that's going to be equal to 32, which is greater than 0, so it's not a saddle point. And if I take my second partial of x, if I plug in 1, 1 into the second partial of x, that's going to give me negative 6, and that's less than 0. So that's a relative max. Finally, I'm going to have my point 0, 0, negative 1, negative 1. And with that matrix over here, so second partial derivative with respect to x is negative 6x squared. If I plug in negative 1 into the x, so negative 1 squared is positive 1. Positive 1 times negative 6 is negative 6. F of xy is equal to 2. There's no variable to plug in. F of yx is also 2. There's nothing to plug in. Second partial derivative with respect to y, that's if I plug in negative 1 over here, this should be a squared. If I plug in negative 1 into here, it's going to be positive 1 times negative 6. That's a negative 6. When I solve it, negative 6 times negative 6 is positive 36. Minus 2 times 2 is 4. So 36 minus 4 is 32, which is greater than 0. Now if I take the second partial derivative of x with respect to -1 plugged in, that's going to give me -6 times -1 squared, that's going to be -6, which is less than 0. So that is a relative max as well. So it's a relative max at -1, relative max at 1 and 1, and it's a saddle point at 0 and 0 because the d value was -4, which is less than 0. Thank you.